goes through a lot of things over 90 minutes. And my personal focus would be on recent findings from various studies we've done, and some of which have been implemented in various design standards. So before I start, I'd like to thank the Institute for Steel Development and Growth, as well as Indian Institute of Technology at Roorkee, for the invitation. And also I'd like to thank the Swiss National Science Foundation, as well as Nippon Steel Corporation, for sponsoring some of the work that you're going to see today. Also, I'd like to thank a number of my students, Professor Ahmed El-Kadi, Dr. Yusuke Suzuki, Dr. Hamad El-Jisr, as well as Dr. Andronikos Skiadopoulos, who are really the people who have done most of the work you're going to see. And I think some of them are professors, some others work in engineering practice, but also some others are following academic path. So there is a diversity in the group, primarily because of the number of things we do. So I will use the first 3 slides to give you a small overview of my activities, and then I will go into the specifics of the subject. So obviously, earthquakes is a worldwide issue, and the reason why I'm presenting this is because mostly work on earthquake engineering. And as we know, earthquakes could really wipe entire cities, such as here in Italy, where you see, a picture before and after the earthquake, after one of the recent earthquakes in central Italy. And if we also look at some of the key statistics, earthquakes usually are responsible for about 28,000 casualties per year, as well as displaced population, which is in the range of 300,000 a year, based on data from the UN Office for Disaster Risk Reduction. And what we are trying to do here is we are trying to investigate the reasons why buildings in particular collapse. And in particular, we are trying to understand first the physics behind the problem. And for those of you who are students, you've seen this multiple times. If you have a building that is subjected to an earthquake, usually a building is going to undergo deformations. And then the external force caused by the earthquake will be equal to the inertial forces plus damping forces, as well as restoring forces. And here, in what I do is, I'm trying to really understand where do the restoring forces come from, and in particular, what could influence what we call degradation, because this term here could be highly nonlinear, and ultimately is basically this that will cause buildings to collapse, such as the image here. So here, the primary challenges in simulating collapse would be to understand what materials do, also to understand what is happening with the nonlinear geometric instabilities that cause softening. And also, we try to generate data where we really try to understand with this data what happens at large deformations where you could get these types of problems. And what I mean by data, I mean some of the data you will basically also see today, where essentially instabilities like the ones that you see here could really cause members to experience what we call local buckling. And then these phenomena would really jeopardize the ability of the system to carry lateral loads such as earthquakes. So with this in mind, the laboratory here at EPFL essentially works on simulating this type of phenomena with advanced models of various fidelities. We do multi-scale experimentation to validate these models. Also, for those of you who may be interested into policy, we have developed methods that have been integrated into software where one could really use the information from the analysis, and essentially you can do simulation assisted infrastructure assessment, where one of the things that we are interested here is because of not only structural damage, but also how losses between components could be contributing to the total financial losses after an earthquake. And putting this all together, we try to also develop new concepts for minimal structural damage, both at the connection, member, as well as the structural system level. And I'll show some of these concepts today. So the type of work we do is not only scientific, but we try to see how we can make contributions to international standards. And we have worked with the National Institute of Standards and Technology in the US, as well as other people in Canada and Europe. And some of the work also essentially has made it to the updating of pretty much all international standards. So without further ado, I'll basically switch now to the topic. So my talk will focus primarily on steel moment frames, which is a very popular lateral load resisting system. And for those of you who may not be familiar with moment frames, they rely on the ability of welded or bolted connections that you see here on the right to dissipate energy during an earthquake. And essentially energy is dissipated primarily due to beam flexural yielding or column flexural yielding that we try to avoid. But also the joint here could potentially be dissipating energy through shear yielding because of the way it's been deforming. So the primary structural elements, as I mentioned, relate to columns, panel zones, as well as the connection itself, but also the role of the slab could be important. So this is why in today's talk, I will focus pretty much on these three effects or members and the effects that we see under cyclic loading. And also I will go into the details on how some of these have informed some of our recent code provisions. So I will first start with columns, and I'd like to give you some motivation related to steel moment frames. So what we know on steel moment frames in terms of design considerations is that they are primarily based on cyclic tests following the Northridge earthquake in 1994 in California, where there was a lot of connection damage or damage related to performance of connections. The other thing is that most of these recommendations emphasize on what the connection performance is at the lateral drift ratio of about 4% radian. And the other thing is that moment frames above a certain height would be controlled by stiffness rather than strength that you typically see, for instance, in a reinforced concrete shear wall. And stiffness will control primarily column design to achieve the target design drifts, especially in the US, where we use perimeter frames rather than space frames that are more common in Europe. So in this case, you may see that the designer will have to use what we call deep sections that are very slender. And the reason why we do this is because we also try to reduce the steel weight to ensure that the design becomes a bit more economic. Now, as I said, when you're looking into connections will typically be controlled by a dissipative zone that will form near the column face here that you see an example from previous test. And what happens in this case is that once you reach this point 2 here on the figure on the right, what is going to happen is that the flexural resistance of the connection is going to experience strength degradation because instabilities such as the one that you see here in the figure will start to become very evident. And flexural strength degradation will also be followed by flexural stiffness degradation. Now, when you have this type of instabilities in connections, this is an example when we are looking at one of these beams pretty much from the bottom, is that for certain types of connections, these instabilities will generally create eccentricities, and these eccentricities create additional torsional demands that could potentially be transferred to the column. So then one of the questions is that, how would the column behave once you have something like this, in addition pretty much the conventional flexural demands that you would have because of the cyclic loading. So columns, of course, as I said, we try to protect them, but if you're looking here at one of the tests that on moment frames that has taken place in Japan about 11 years ago, usually moment frames will be vulnerable at the bottom stories. And if you keep track of what happens here at the bottom stories, so when you have seismic loading coming in, we anticipate our beams to develop plastic hinges because we try to protect the column. But what happens here is that if we get an earthquake that the seismic intensity is higher, usually what is going to happen is that at the locations where we anticipate to have damage, there is going to be strength degradation because of local buckling that I showed in the previous slide. And that will create redistribution in the members, and it will, of course, increase the flexural demands in columns. And eventually, depending on the severity of the event, that could naturally lead to plastic hinging in the columns. Now, when we started this project about, I would say, 14 years ago, we reviewed the available experiments on steel columns, and we surprisingly found out that most of the tests that had taken place till then were in fact on sections that were either very small and essentially you practically never use, such as the test done by Professor Popov in 1975, or the ones done in New Zealand by Professor McRae, or the ones done in Japan by Professor Nakashima. Only till 2006, where Professor Wang at the University of California in San Diego tested columns here that are quite heavy, but they are meant to be used in braced frames or frames with buckling restraint braces, you would get to something reasonable that is actually used in buildings. So this essentially told us that we practically have no test data on actual column sizes that we actually use in buildings. And for this reason, we tested several columns ranging from here, W14, that would be about 400 millimeter, all the way to about 600 or 700 millimeter deep columns. We also tested the columns that were hollow structural steel sections, or HSS. And here, this comprehensive table essentially leads to about 50 specimens in total, where you see that we varied the primary parameters that you would like to get an idea what they do once they vary in terms of web slenderness. We also varied the loading scheme. Besides the traditional unidirectional loading, we also have the chance to do bidirectional loading. And also we tested columns with different materials so that we can capture also the effect of material into our assessment. So in one of these tests, I will show you, this is a test. So here you see a column that is about 4 meters tall. It's about 600 millimeter deep. Here in the east local view, you see pretty much the fixed base at the dissipative location, pretty much at the base. Here you see in the north local view the flange, and then with the graphs here you see synchronized the moment versus rotation and the axial displacement versus rotation that we see here at the bottom right. So what happens here is that the column, while it goes into lateral deformations, in the presence of axial load, you see that essentially it behaves quite well, up to about 1.5 to 2% drift, where you see that from pretty much here, the east local view, that once you have instabilities due to flange local buckling, then we have significant strength degradation that could ultimately lead to almost complete loss of the lateral load capacity at about 4% drift. And of course, this picture was quite concerning because, as I said, at this location, we anticipate plastic hinging. And the other thing that is observed here is that the column is also moving vertically because it experiences axial displacement or axial shortening, we call it, because the column supports the floor system and the load that is there is not moving while the column is damaged. So that would naturally make the column sit. Now, if you want to look at this problem a bit more closely, this is another video where again, this is a different test where essentially here it shows that axial shortening will happen once instabilities occur near the fixed base. And you see that, the column could distort quite severely, primarily because the axial load will really need to be transferred to the footing. And because the column is connected to the floor system, obviously, it would naturally cause this issue. Now, we've tested multiple cross-sections, and you see that when you're looking into hollow sections versus wide flange sections that I showed earlier, you still have the same problem. And the only difference would be that the shape of local buckling could be different depending on the cross-sectional slenderness. And here on the figure on the right, you see that for a relatively compact column, the shape of local buckling is what we call the elephant foot. Now, this issue of column axial shortening was quite concerning back then because, as I said, till then we didn't have a lot of information to kind of highlight this problem. And then recently, like a few years ago, there has been an earthquake. There was an earthquake in Mexico in 2017, where, for instance, one of the buildings there was a steel building with hollow sections that you see here. And these hollow sections were relatively slender. And what happened here in the fixed end column base, this image was taken 4 days after the earthquake. So you see the local buckling here happened and the column was slightly shortened because here this was a box column with welds in the corners. The welds also essentially experienced fracture. And 51 days after the earthquake, after multiple aftershocks, you see that the column experienced complete squashing because of this issue of axial shortening I raised. So notice that the residual story drift in this case, which is related to lateral deformation, was nearly zero. So under normal circumstances, if this building was not experiencing this type of issue, it wouldn't be demolished. With this in mind, we tried to kind of look at several aspects related to column design as well as column performance. One of them, I guess it's a good thing, is that we monitored well in some of these tests that I showed what would be the performance of welds near the base location. And in most of these cases, we used the complete joint penetration weld with the detail that you see here for one of the tests, including weld access hole that minimizes residual deformations. But in the presence of the axial load, you see that the columns are damaged away from the weld region. And if you actually monitor what would be the engineering strain near the welded region, you see that once you have local buckling forming away from the weld, what happens here is that the strain demands near the welds would actually cap and that would mean that welds are not going to be pushed a lot as we originally thought. So that by itself means that we could consider simplifying some of the weld details in the fabrication process here without having to use very expensive welds that in this case would be complete joint penetration welds. Plus the fabrication detailing could be a bit simpler, which is, I guess, good news if you're looking into pushing the steel construction in, let's say, projects related to development, or let's say the projects related to the construction of new buildings. A couple of other things that we found that may be interesting is that we reviewed carefully what would be the influence of the loading history. And here you see tests on 3 identical columns. One of them is tested monotonically. This would be the black solid line here. The other one would be tested under symmetric cyclic loading history that you see at about 4 or 5% drift. The column will lose the entire resistance. But then there is this other protocol that we've tested that is called the collapse consistent, that represents demands on columns from what we call near fault ground motions that we anticipate to be the most dangerous. And in this case, you see that although the column would lose the lateral load resistance, that will happen at a very large rotation, about 3 times more than what a typical symmetric cyclic loading protocol would tell us. Also, we've looked at the same exact problem for regions that one may anticipate what we call long duration events. This would be, for instance, Mexico City that I showed earlier, but it would be if you are in the US region close to Oregon, or if you are in Canada, the Vancouver Island. And there you see that, this aspect of the loss of the strength of the column at a relatively small drift would be evident because of the very large number of inelastic cycles. Also, we looked at the effect of the axial load, and in particular variable versus constant. And what happens here is that when the building is deforming, if you're looking at columns, there would be columns that essentially experience tension, but in this case, you would worry more for the foundation system. But there would be columns that you would experience more compression. And then because the phenomenon is cyclic, you have dynamic overturning effects where the column in compression will eventually become column in tension. Whereas the one here in the middle essentially would experience, maybe I highlight this one in the middle, it would experience more of a constant axial load compared to the others. So in this case, what we saw is that when you have a column under constant axial load versus the one under variable, essentially the one under constant axial load will behave worse because what happens here is that the axial load remains in position, and because it doesn't fluctuate, the neutral axis position more or less remains the same. And because you don't have this sort of variation of the neutral axis position, ultimately this leads to the column to lose its load carrying capacity at a much earlier or smaller rotation compared to the case that you have variable axial load. And you see that, for instance, at 8% drift in this case, the column is able to sustain about 30% of its reserve capacity. Coming back to axial shortening, we've also looked at that axial shortening will vary compared to constant and variable axial load case. And here you see a case where that would naturally create differential axial shortening between an edge column and the middle column. And in particular, if you're looking at the interior column, you would have quite substantial axial shortening, whereas in the case that the axial load varies because of the overturning effect, the tensile loading would naturally try to straighten the member. And then, if you're looking at adjacent columns, that differential axial shortening could potentially create what we call catenary action that you see here in the beams. And this catenary action is something that we don't usually design our beams for when we size the connections, because we think that the beam will always remain the same position along the entire length of the frame. But in reality, this is not going to be the case. So this is why you have to also pay attention to what the slab does, but also how can we minimize shortening from the columns that I showed you. So to further study this problem, we also conducted the simulation studies that you see here, an example where we used validated continuum finite element models, and we used some of the test data I showed earlier to validate these models. And these models are validated quite thoroughly. I mean, for those of you who may be interested about this, we are using cell elements, but also we have solid elements. We have used solid elements. We are inserting imperfections due to manufacturing, but also due to the product manufacturing itself. We are taking into account residual stresses because of the hot rolling, but also we are taking into account plasticity because we anticipate the plastic deformations at the material scale. And I'll be happy to talk more about this if you have questions, but for now I'll try to kind of stay away from some of these details. But with some of these models, we were able to study pretty much columns in more detail and propose what we call design recommendations, where we can prevent some of these problems I showed earlier. So in particular, here you see an example where we try to identify what would be the corresponding rotation based on simulation at which the column is not going to lose more than 20% of its peak resistance. This is a characteristic point for steel construction if you look at, for instance, connections. And here you see that when the web slenderness of the column is actually being increased, there would be a point that is around 30 or so, or 35, where you would get, for a given axial load ratio, a bunch of cases that essentially this 4% target that we anticipate in connections is not going to be fulfilled. So to address this problem, we propose to reduce the current slenderness requirement according to the American provisions by about 2/3 for the web compactness, but that would be only for the first story steel columns where we anticipate to have a dissipative zone near the fixed end. Another way to address this problem would be to impose an upper limit which is 30% on the gravity-induced axial load ratio, not the overturning, but the gravity, for a first-story steel column. And again, if you are dealing with ductile moment-resisting frames, this is something that has been adopted by the Canadian provisions. And also the 30% limit here is something that, at least for typical steel moment frame designs, you could easily satisfy. So it's not a big restriction. It's just something for the designer to keep in mind, and perhaps consider increasing maybe a little bit the size of the column to satisfy this limit, again only for the gravity-induced axial load ratio and not for the total overturning effect that of course could go higher. Also, we made some design recommendations that have been adopted in the new revision of Eurocode 8 related to some of these problems. That this code is going to appear, I would say, later this year. So for wide flange or HSS, again, the axial load ratio in terms of gravity-induced axial load ratio should be limited to 30%. And for encased or partially encased or filled composite columns, this could also be interesting for high-rise buildings. Here, the limit could be quite generous, and in particular, it shouldn't exceed 75% of PY. Notice here that in this case, you may experience problems in the corners, primarily because for field composite members, we may use very slender profiles. And in this case, we anticipate to have this problem if the axial load goes very, very high. This kind of wraps up the first part of my presentation that relates to column behavior, as well as some information that eventually I think is important for everybody to know. And then also I close the session with some of the design recommendations that I showed you that relate to slenderness, as well as limits on axial load ratio that we think could actually work quite well for typical design cases that we may be dealing. Now, the next subject that I'd like to talk about that relates to seismic stability of moment frames relate to the panel zone joint or the panel zone. And in particular, I will first talk a little bit about the behavior of the panel, and then I will talk about some design models that we typically use, and some improvements that we've done to leverage the beneficial aspect of the panel zone itself. So panel zones date back, or research on panel zones date back from 1970s, where in fact my mentor, late Professor Kravinkler, studied with Professors Popov and Bertero at the University of California at Berkeley. And this work showed that panel zones, in fact, could be quite stable. And in particular, if you're looking at panel zone shear force versus panel zone shear distortion, you can have quite substantial energy dissipation. And if you're looking also at the global response, you see that within a story, at a very large lateral drift demands, you see that beam to column joint could experience no degradation, primarily because the panel zone itself would dissipate most of the energy, and as I said, the behavior of the panel zone is quite stable. There has been recent work by Professor Engerhard at the University of Minnesota, where he showed also highlighted the difference between cases where the panel zone remains elastic, and here you have a code compliant case where the panel zone remains elastic, but when you are looking here at the story shear resistance versus story drift ratio, you see that at the drift level on the order of 2.5 to 3%, we start having unstable behavior, primarily because here you see that the beams would experience local buckling, and because of these inelastic distortions, essentially you're going to have strength degradation. Now, Professor Engerhard tested also the case where the panel zone here is highly inelastic, and you see that if I am actually projecting the lines here at the same level of rotations, representing design level of rotations, you see that in the case where the panel zone becomes inelastic, I have no degradation at the same level of rotations. And if you inspect here the figure, you see that the joint itself has experienced some yielding, but that essentially is accommodated by flacking of the paint. But if you're looking here on the beams haven't experienced significant damage. So leveraging panel zones in seismic design could potentially be useful, because you could also minimize structural damage in the adjacent beams, and that would in fact help the building be back on track if we're looking at deformations that are not, let's say, very excessive. Now, to leverage the shear yielding of the panel zones, obviously one has to look at what would be the current design models that we're using. And if you go look at some of these models, essentially the main assumptions would be that only shear deformations would be considered, similar to what you see here in this figure. We also assume that panel zone yielding will happen in a uniform manner, And also we assume that, once we reach what we call the 4 times the yield distortion of the panel zone, the panel zone will reach its plastic resistance. And essentially after this point, you're not going to have any other contribution from the flanges. However, these models have been proposed for cases where the columns come with flange thicknesses that are less than 40 millimeters. And of course, if you have columns with thicker flanges, that may not be the case. So to look at this problem in more detail, we reviewed all the test data on post-Northridge connections. That essentially these are test data that happened after 1994. And we have collected all the data into what we call a database that you can all download from this link here if you use your cell phone. That will point you to the website. And here what you see is that we have the possibility of, in fact, reviewing the test data with what we call a parallel axis plot by taking into account parameters that, in fact, affect the panel zone behavior. And while the current allowable limit essentially is, as we said, at 4 gamma y, you see that we had the substantial number of cases where the panel zone, in fact, yielded a lot more, and that these are very interesting cases because these could provide additional insights into models for panel zone design, but also behavior of connections that panel zones dissipate more energy than what the code allows us today. So with this data, we assessed the available panel zone models, and here you see a comparison on what we call the panel zone stiffness that has been highlighted here in this figure. In one of these tests, that would be the slope here, the elastic stiffness. This stiffness is important to have correct because if you are designing a frame and you would like to have the evaluation for drifts, you want to make sure that the elastic stiffness of the panel zone is correctly captured. So what we found is that when you compare with pretty much modern codes such as the American but also the European code or other panel zone models that have been proposed in the literature, there is a deviation with the test data that essentially there is deviation with the test data that essentially tell us that the existing panel zone model in terms of stiffness is actually quite off. Similarly, if you're designing for strength, what happens here, we are interested on the contribution of the panel zone at 4 gamma y, where the flanges also are contributing to the resistance. And what here the graph shows us is that if you pretty much compute the panel zone resistance with the available code model, or you use another model available in the literature, and you normalize with what we measure from the tests, obviously, if these models would have been good, then all the data would be around 1. But you see that, once you go into flanges that are above 40 millimeters, you could have cases where the panel zone strength is actually under-predicted by about 40%, which is quite substantial. So we had a fresh look into the problem. How by leveraging finite element analysis again with some standardized models that we have. And here you see one of the tests from those collected, where you see that the model that we have is able to replicate well the inelastic behavior of the panel zone as measured for one of the tests in the literature. Whereas the anticipated model that is being used in design under-predicts, as I said, both the stiffness, strength, as well as strength at 4 gamma y, which is pretty much the allowable limit by code today. And with this model, essentially we were able to retrieve or look well stress distributions within the cross-section. And with these stress distributions, we saw a number of interesting things that we tried to kind of articulate within new models for stiffness and strength. So the first thing we saw is that for panel zone geometries where the aspect ratio of the beam versus the column starts to become above 1, you have also the bending deformation of the flange here that becomes important in addition to shear of the web. And you can, in fact, nicely combine them if you assume that these work in series, and essentially the panel zone stiffness can be computed by combining both the CR and bending contribution. And if you actually compare how the predicted stiffness is in this case versus the ones measured from the test, you see that most of them lie on this 45-degree angle. So basically we have practically almost zero error compared to what I showed you earlier that was in the range of 20%. Now, if you are looking at strength, we found a number of interesting things related to the column itself. So for instance, if you are using columns that are deeper, these naturally will have more slender flanges. And if you pay attention here, you see that the flange contribution in this case is not going to be important. Also, the other thing that we observe is that if you have a deep column, the assumption of a uniform shear distribution is actually not quite correct, because in reality, that's what we anticipate to see in the web. But if you are looking at columns where you have more stocky cross sections, then what happens is that, again, if you are looking at the flange contribution, now starts to become important. So for these cross sections, the panel zone models should be definitely revised. But also, if you are looking at the web, here you see that the assumption of uniform web stress is actually true only for the case of stocky cross section. So with this in mind, we proposed a new model where a designer could predict the panel zone strength. And this model has been separating the web contribution from the flange contribution through these two factors here that you see. One is referring to the web, the other refers to the flange. And you can, in fact, compute these factors explicitly. So how can you do this? So we have made a proposal that has been adopted to the Canadian code as well as Eurocode 8 part 1, where you can actually compute this strength here by taking into account the web and flange contribution. And here you can measure how much the flange contributes relative to the total contribution of the panel zone through this ratio here. And this ratio can be explicitly computed through these expressions here that are analytically derived, that essentially relate to material properties such as the Young's modulus or the Poisson ratio, and also geometric properties of the column cross-section, such as the flange thickness and the width of the column, as well as the moment of inertia of the column, or the corresponding thickness of the doubler plate that you may want to insert there to ensure a certain resistance. Moreover, this proposal here is taking into account the influence of the axial load through the coefficient AC here. And depending on the axial load ratio that we have, this coefficient could be simply 1 or could be taken into account through a regular von Mises criterion. Now, if you ask yourself, how does this model compare to the available data? So this is the model by the AISC, as I showed earlier, and notice here the very large overestimation of this data. But when we, in fact, compare the proposed model with that of the AISC, you see that, we can reduce the error by about 40% in this range. And notice here a small variation in the predicted strength. This is because here we compare with direct measurements from prior tests. As I mentioned, the model has been adopted in the second revision of Eurocode 8, Part 3, as well as the Canadian provisions. And this is one of the work we've done that received the Raymond Reese Award because of the impact to design. So I'd like to mention a couple of additional things related to panel zones, and in particular, how can we also consider simplifying details associated with the way we form welds in pre-qualified connections. So in pre-qualified connections, if you focus here in this region that I'm highlighting, what happens here is that you may anticipate problems with defects because of welding. So that would be what I call location L1 and L2. Or you may anticipate problems with laminar tearing in location L3 because of the through thickness properties of the column flange. But this L3 should not be the case if you use materials with proper notch toughness in the through thickness direction, which is something that we can do today. Now, for the other two locations, for those of you who may be more interested in fabrication, usually we use what we call this backing bar here, or a small steel plate, where we put it usually to support the welds. And from what we know, this is a location where usually you will have to be a little careful and in fact remove this plate after the completion of the weld because it creates this sort of flow that could vary over the width of the beam. And this is why we have to remove this plate and inspect pretty much the weld on the back. However, all this procedure of removal and inspection and then potentially repair, it could be time consuming, but also could be cost ineffective. So we try to work out on a detail where we can see if we can keep the plate in place and at the same time minimize the fracture potential. So for this, we studied the problem again through the help of detailed finite element models. In this case, these are sub-models where you see that this entire region is being carefully modeled. And what we did here is that we paid attention to the potential flaws that you may have near the backing bar here. And with conventional fracture mechanics, we tried to see if there are ways where we can reduce the fracture potential of these connections by changing the geometry of these plates. So here you see an example where we look at one fracture metric, which is the J integral. And we see here under monotonic loading that once we have a conventional backing bar and we leave it in place, once the joint reaches about 1.5 to 2%, the J integral will match the capacity of the weld, and then obviously at this point we anticipate to have fracture. Now, what we did here is that we developed a new backing bar where it's actually beveled. So you see here the bevel, and with this trick, what the bevel does, it moves away the flow from the primary weld that you would like to protect. And if you actually repeat the process and you don't remove the weld backing bar, what happens here is that in fact we can reduce the fracture potential by about 6 times, and you see that the same connection that experienced fracture at 1.5% or 2% drift, now it can actually go to about 2% drift, 6% drift, and in this case, it's not going to experience any fracture. So we've tested the concept, including the highly inelastic panel zone that in fact could augment this sort of fracture potential in this location. Here you see pretty much how our bevel backing bar looks like before we pretty much complete the weld here. The goal of the experimental program was to demonstrate that we can achieve stable hysteretic response because of panel zone yielding up to very large drifts. Also to prevent beam local buckling because we dissipate more in the panel zone, and in fact prevent beam local buckling up to about 5% drift, and then of course show that the beveled backing bar I just showed, if we leave them in place and we don't remove them, that in fact is not going to cause any problem in the welded region there. So we conducted full-scale tests with our collaborators in Japan, Nippon Steel Corporation, where you see here the beam or the beam to column connection. The column is in this position, is experiencing axial load that is about 20% of Py. And then with the hydraulic actuators here, we are able to apply the cyclic load on the beams. And I'm going to show you one of the tests where here you see pretty much the sub-assembly being loaded. Here you see what is the backing bar at the bottom and from the west side of the beam and the east side of the beam. And then here you see what the panel zone does. So what happens here is that you see that up to about 2% drift, my panel zone has dissipated most of the energy, but then when I inspect both the beam as well as the panel zone as well as the backing bar, I see that practically it shows no damage because energy has been mostly dissipated through shear yielding. And here notice that the drift level, which is about 2%, this is what we use as a drift limit in our design standards when we are looking into the design basis earthquake. Now, if we keep loading, you will see that obviously the panel zone will experience more inelastic deformation, but notice how substantial is the story shear resistance and essentially no sign of degradation, even at 4% drift, which is essentially the limit according to the AISC pre-qualification criteria for connections. And again, you see here no local buckling in the beam. You see no damage in the near the bevel. And also if you're looking at the panel zone, of course, you see that the panel zone has distorted more, but essentially this is only flacking of the paint because of shear yielding in the panel and nothing else. So if we keep loading this, in fact, we cannot accommodate excessive inelastic deformations in the panel zone that exceed far the limit that we anticipate according to design, which is 4 gamma Y. Notice here that we are already at 15 gamma Y, and the joint itself shows superior performance even at 6% or 7% drift. At this level, we have some initiation on local instability and some yielding near the backing bar, but that doesn't mean that our connection doesn't dissipate more energy. In fact, we pushed it even further to see at what point we are going to have the ultimate failure mode, which only became evident after 8 or 9% drift and at shear distortions that exceed 20 gamma Y, in fact, nearly 30 gamma Y, which is quite substantial. And here, this is an example where you see that, the beam to column connections designed with panel zone joints exhibiting shear yielding could in fact demonstrate superior performance relative to what we actually do today, including also the potential use of beveled backing bars that minimize fracture potential at this position. Of course, we kept testing till we had the ultimate failure mode, which was ultra low cycle fatigue in this case, at the position where we in fact damaged the connection more. But this happened only at about 9% drift, as I stated earlier. We also did some additional work on exploring the beneficial aspects of shear yielding in the panel by looking into moment frames designed between 4 to 20 stories We designed about 32 buildings in urban California. We varied here the number of bays from 3 to 5. We also looked at variable panel zone targeted distortions. One here means elastic design, but I think you should pay attention to what's happening at 10 gamma Y, which is appreciable dissipation in the panel zone. And the modeling approach here, for those of you who may be interested in modeling, essentially included the panel zone itself by using the model I showed earlier in my presentation to model here panel zone yielding. The beams also incorporated the strength degradation that you see here based on prior work that I've done as part of my PhD thesis several years ago. But also more recent work related to columns. So we also included degradation in columns in case that columns were damaged. So we pay attention here into a couple of damage indicators. One relates to what we call the collapse risk evaluation through the use of collapse fragility curve, we call it. And this fragility curve for a 4-story building here shows that if you are looking, for instance, at a spectral acceleration of about 1g at the roof of the building, you see that, the conventional design where the panel zones remain elastic would have a probability of collapse on the order of 12 to 15%, whereas the design with inelastic panel zones is going to reduce this by at least a factor of 2, and you would have the probability of collapse in the range of 5% or so. Moreover, for those of you who are doing work on demolition or demolition after earthquakes, one of the aspects that we pay attention is what we call residual story drift after an earthquake. And here you see that if we compare for a design level earthquake, what would be the annual rate of having residual deformations that could be potentially problematic for demolition, you see that when the panel zone, in fact, experiences about 10 gamma Y in elastic shear distortion, you can get a reduction on the residual story drift of about 30% relative to pretty much the conventional design that we do today that more or less anticipates elastic panel zone behavior. This is more general if you are looking at residual drifts for pretty much all buildings we looked, 4 to 20 stories. You see that when you're looking at residual drifts and you compare what's happening at elastic design versus inelastic panel zone design, you see that you can get a considerable reduction on the residual drift, primarily because of the beneficial aspect of shear yielding that essentially creates or has increased hardening because of the kinematics of the panel zone deformation. So hopefully, this convinced you that, panel zone shear yielding could be beneficial. We could maybe, think about connections and the way we design them a little differently. We can also simplify welds or think about weld detail alternatives that could reduce cost. So now the next subject I would like to talk about relates to composite construction, and in particular, composite steel moment-resisting frames. This is a system that obviously it's popular at various places around the world due to its enhanced lateral stiffness and strength because of the composite action. And it could potentially lead to lighter steel designs if you leverage higher degree of composite action. But of course, there are concerns, for instance, near the dissipative zone here. A lot of people think that, we should not use the composite action. But the question is, if we see any problems related to this. But there are also other issues related to design. One of them is what is the right effective width, okay? So for instance, in this table, you see that if you look at, for instance, the European norm or the American norm or the Japanese norm, you see that each one of them has different rules for the effective width. And you see that, for instance, the Eurocode has a very detailed recommendations compared to, for instance, the Japanese code or the American code that is quite minimal. So that one of the questions when we worked on this project is, what is really the right effective width to use? And does it matter if you have a very detailed rule to quantify the effective width versus cases where, these rules are actually much simpler? So another question that arose prior to the completion of this project was related to the strength of our shear connectors. So in seismic applications, if you recall, we use a penalty of 25% reduction regardless of the beam depth. And obviously, this rule is there for safety, but one question, but obviously, if you think about economy, that will increase the number of studs that you're going to have to achieve a certain degree of composite action. And of course, that will increase the cost besides some practical matters that relate to the corrugated steel you may be using and the spacing you may have if you basically have a lot of studs. Moreover, you have to use headed shear connectors that have to be ductile, so the height over diameter would be equal to 4 or at least 4. And of course, the deformability here is has to be larger than 6 millimeters prior to the loss of our shear strength on the studs. Now, these recommendations have been put in place based on shear stud testing from typical push-out tests that you see here in the figure, where essentially we apply either monotonic or cyclic loading. But one of the problems with this configuration is that once damage localizes here in the studs, because this configuration cannot redistribute loads, what happens is that the damage that we see could be more excessive than it is in reality in actual buildings. So another issue that for those of you who may be experienced with the Eurocode is that when you design composite steel beam, you have to be a little careful with the preventing crushing from the concrete. And essentially, you would like the bottom flange of the beam here to yield and be damaged prior to concrete crushing at the top. So in Eurocode, there is this relationship here that essentially tells you that if you're using a strength reduction factor of a certain value, that will impact what the dissipative zone will do. And obviously, that requirement here is going to become more strict. However, I'd like to show you something that we have found. So here, this table shows you typical European cross-sections ranging from IPE 270 to IPE 550. So these are, let's say, different beams that you could potentially use in design. In the vertical axis here, we increase the strength reduction factor, or Q. And what happens here is that once you go to Q values or strength reduction factors larger than 2, practically most of the beam cross sections, regardless of the length that we are using, become unavailable because this requirement that we have to satisfy here actually cannot be satisfied. So only here the region that is not shaded with red would be the allowable design of hot rolled profiles that we can use. And obviously, if you go to larger Q values, that could be typical for highly seismic regions, you see that technically we have to use a built-up shape rather than a hot-rolled shape because here none of them will literally satisfy the requirements. So this happens for a few reasons, because in current provisions, these rules have been formulated by assuming that concrete crushing happens by neglecting the fact that there is a reinforcement on the slab. So 2.5 mil in terms of concrete crushing strain. And of course, this is very restrictive for seismic designs of composite steel MRFs if you want to use a Q factor that is larger than 2, which is in fact common to use, at least in the US. So for this reason, we decided to do a very thoroughly designed test where we, in fact, tested part of a 2-bay composite moment frame designed with typical steel and concrete materials. This was designed in a highly seismic zone that essentially was on site class D in Sion, Katerini in Greece, Braila in Romania, Rimini in Italy. So basically this location could be typical across Europe. The degree of composite action was 80%, not 100%. We assumed a strength reduction factor of 3. We waived the 25% reduction in the shear stud resistance because we wanted to see if this requirement is absolutely necessary. We used the stiffened end plate beam to column connections, and the fabrication essentially was not was actually a fabrication that respected execution class 2 according to the European norm 1090-2 that is very typical in Europe. Here you see a cross-section of the composite cross-section where the effective width we assumed was actually much larger than what the code tells us, so that we can really see also what is the actual effective width we had. So the test structure here was a 6-story building that we basically tested because of space limitations, only the bottom part that you see here highlighted. And here you see the white frame is basically the 2-bay frame that we considered the slab, including the transverse beams that we had to support the beam laterally. You see that the height from inflection point to inflection point in the column was about 5.5 meters. The test structure was loaded through very large servo-hydraulic actuators of 2.5 meganewton with a very large stroke. And as I mentioned, the total length of the specimen was about 10 meters. So here you see the figure when you're looking under the frame after the completion. And you also see here the transverse beams that we also took into account. And basically here you see the corrugated steel under the slab. This is another snapshot just to kind of appreciate the scale. Again, looking from underneath. And here you see the dissipative zone. This is a snapshot from one of the tests, but I will show a few more details in the next few slides. So here, a few things on instrumentation. We used digital image correlation system that was basically 8 cameras, 2 per location that you see here near the column, because we wanted to track strains on the slab surface near the dissipative zone. We also used the fiber optic cables where the reinforcement here was actually longitudinal reinforcement was instrumented to measure continuous strain over the reinforcement. This is important to track the effective width. We also used the LED system to track displacements, especially at large deformations. This is very important because this system can give you displacements in a wireless manner. But also we used conventional instrumentation. In total, we had about 360 sensors. So in terms of load protocols, we did a conventional symmetric cyclic loading protocol up to about 4% drift limit to see if we are respecting the pre-qualification limits according to the AISC provisions. And then we subjected the test structure into very severe load protocols, such as the SAC near fault, as well as what we call a collapse consistent loading protocol. And the specimen essentially was subjected up to about 15% story drift ratio, which is quite substantial if you think about, what could happen in an earthquake. So this is an example from the first protocol. So you see here that, if you're looking at 4% drift limit, our frame respects the pre-qualification limits very easily. In fact, you see that, we haven't lost much of the total shear resistance. Near the dissipative zone, although we leverage the composite action, you see that, the dissipative zone behaves exactly as anticipated, where you have plastic hinging near the bottom flange and no indication of other failure mechanisms that could be potentially attributed to the slab, which is good. Also, we pushed the frame here. You see a snapshot just to appreciate the scale. And we pushed the frame to very large deformations. And as I said, we monitored here this location relatively well, both from the top as well as the bottom, but also inside the slab. And you see that, the frame could sustain excessive deformations that eventually lead to crack developments, but only at the very, very large drifts. But still, in fact, the composite action is beneficial because it holds the frame in place. And even in cases where I have huge cracks, the slab, in fact, holds the frame in place through an axial load that essentially is passing through the slab. Here you see what happens from the top, and I'm having bearing on the slab, which is basically all fine. And the strain distribution, the strain distribution that we saw essentially matched relatively well what we anticipated. So let me, I clicked accidentally. So a couple of things that you may be interested. One of the things that we measured that there's not much data available, and I think it's very important, is what's happening with the slab width. So here you see that we measured explicitly the slab width by actually using the direct measurements both on the reinforcement as well as the top surface of the slab. And you see that the slab width, in fact, increases while the drift increases. So you see that, what we know by code, in fact, is at about 2% drift. The proposed value according to the AISC provisions as well as the Eurocode provision in the next generation matches well what we expect. Plus, we cut the slab with a diamond saw, and basically we see that these values here correspond to more or less what we observe from our section cut here at larger deformations. Now, based on this information, as well as information that comes from what we call the digital image correlation system, here you see how the strains distribute from the top surface of the slab at a story drift ratio of about 2% that corresponds to the significant damage limit state according to Eurocode 8. And we see that, crushing, in fact, doesn't happen to confined concrete prior to 4.5 mil, which is quite larger than the 2.5 mil that I think relates to unconfined concrete. And with that, we were able to, in fact, propose a new table with more relaxed limits for ductility requirements for composite steel beams, where we take into account the variation of the strength reduction factor, but also we take into account the variation of strength. And these would lead you to designs that you can use a lot of the hot rolled sections that before were not possible to use. Few words on the stud behavior before I jump into the very last subject. So what you see here is that we see how the shear at the beam slab interface versus slip changes. And what happens here is that when you have cyclic loading, what happens is that if some of the studs are damaged, what happens is that there is instant redistribution that leads to the system engaging more studs because of the variation of moment within the beam. And that would naturally increase the shear resistance depending on the load increment you're looking. But what is important here is to also correlate this with what we discussed earlier with the 25% reduction on strength that we usually put as a penalty in seismic provisions. And for this, what we did is we cut with a diamond saw the beams so that we can inspect the studs after the end of the test. And what happens here is if you look at some of the studs, or if you look at all the studs, you see that technically after the end of the earthquake, although here we didn't put the penalty of 25% on the shear stud strength, you see that studs are practically undamaged because the deformation that they underwent was actually much smaller than what we anticipate by code. And as I explained this earlier, the reason why we see this is that here the entire beam works together. It's not two studs are taking the inelastic deformations. And this is why if you contrast this with a typical push-out test that in fact we did for this as well, you see here that in that case, studs will actually deform near their base, and that would naturally lead to fracture of the collar. But this we don't see when we actually look at the real condition, which is pretty much the beam that I showed earlier, rather than testing a push-out test that I think the whole Eurocode provision is based on. So again, this is the reality, and for composite beams with beam depths smaller than 500 millimeters, in addition to the test, we've done several simulations, and we've shown that the 25% reduction on shear resistance can be waived, and this has been adopted in Eurocode 8 Part 1.2 as part of the seismic requirements for composite systems. If you are more interested about developments on composite systems, recently the Earthquake Association of Earthquake Engineering, European Association of Earthquake Engineering, has done a webinar program where you could actually watch online for free. But if you are more specifically interested into composite steel concrete frames and all the revisions, you can watch the video here, and also you can download the slides from the same link. Also, you are more than welcome to contact me, and I'm happy to share more information if you have questions. Now, the last thing I'd like to talk about before I finish, I think I have 10 more minutes, is some work that we've done that again has made it to the code that relates to practice-oriented models for seismic assessment of existing structures. And here, some of this work has impacted both the ASC 41 guidelines for seismic evaluation and retrofit of existing structures, the newly developed seismic revisions for evaluation and retrofit of existing structural steel buildings that is put together by AISC. So this is AISC 342. As well as the new Eurocode 8 Part 3, which essentially now relates explicit recommendations for steel systems. So this work essentially relates to the fact that some of you may be called to do assessment of an existing structure, and if you use a program, commercial program, that essentially has the ability to model beams, columns with what we call springs, you will have to construct a backbone curve such as the one that you see here, where parameters A, B, and C will have to be known for different structural components so that you can have a reliable model to conduct your assessment. Now, the existing Eurocode 8 Part 3 had a very simplified way of doing this, where, for instance, here you see that my plastic rotation capacity for beams or columns is simply expressed as a function of the yield rotation and nothing else. The only thing was some classification based on the cross-sectional class. Now, when we started this, a few years ago, we tried to see what these requirements mean based on some available tests. And here you see that in one of these tests where the beam was an IPE 300, if you compare what the Eurocode 8 Part 3 would tell you, you would see that, you kind of overestimate considerably what would be the plastic rotation capacity of this beam. But also another thing that you see is that usually beams would have a good post-buckling behavior after the onset of buckling. And obviously with this branch here, you cannot capture this behavior because essentially this says that the strength of the beam is completely lost at this level of rotation. So to address some of these problems and create more rational assessment models for existing structures, we put together about 1,500 collected experiments that range from material scale, connections, columns that you saw earlier today, columns also with hollow structural steel, braces, as well as I showed you earlier, beam-to-column web panel zone. And we tried to develop rational assessment models that could reflect what some of these experiments show. Also, you can find more information for welds that were from the 70s, material properties for, let's say, very old steels that are all there. Today, I will talk a little bit about pretty much columns that I showed earlier. So as I said, we developed resistance and deformation models for assessment that essentially try to mimic what some of our experimental data show here with a highlighted first cycle envelope. And we fitted to this envelope a simplified multilinear curve where with some statistical procedures, let's say, we try to develop expressions where we can predict our plastic rotation capacity or post-buckling rotational capacity or what we call ultimate strength here would be for different structural elements. And these models would look like that. So essentially for each component now, you have a resistance model as well as a deformation model. So the resistance model will give you pretty much the effective yield strength and ultimate strength by taking into account aspects related to axial load ratio or lateral torsional buckling of your element. And deformation models to predict pretty much the plastic rotation capacity of various elements would be a function of geometric properties of the cross-section, such as the web slenderness or member slenderness, as well as the axial load ratio. Notice that all these expressions come with a coefficient of variation, so that you can know how much variability you have, and you can perhaps use or put a penalty there if you don't feel comfortable with the mean values that essentially are in the code. So if you compare some of these models with what I showed you earlier, so essentially the green would be what is currently in Eurocode 8 Part 3. The red would be what is the proposed and adopted. And you see that, for instance, for this example I showed earlier, now we have the possibility to capture much better the plastic rotation capacity at which we anticipate to have buckling, as well as the post-buckling behavior of the beam that is much smoother relative to what current Eurocode or other models tell us. So again, if you are interested about assessment models, you can follow another webinar program that we recently completed. And again, all links related to concrete, masonry, or wood, you can find from here. But if you are more interested about composite steel, concrete frames, or steel frames, you can use this link here. And again, the slides are available if you actually use the corresponding link to the seminars. So that brings us to the end. I have 3 minutes left, so I'll make a small summary here. So today you saw a bunch of things. The first one relates to seismic stability of columns. You saw that axial shortening as well as coupled instabilities could be evident, and we made proposals to limit the compressive axial load ratio and the web slenderness to kind of minimize the impact of axial shortening in certain column configurations. We also saw the influence of the loading history and the difference between a subduction versus near fault ground motion. We also talked about beam to column web panel zone joints, and here we saw that existing models do not work well with columns having thick flanges and beam to column depth ratios larger than 1. We saw a new model that was proposed for design of the panel zone joint that addresses all previous limitations over the last 50 years. When it comes to composite effects for seismic action, we saw that the additional 25% reduction in shear resistance can be waived for beam depths smaller than 500 millimeters. We saw new recommendations for effective width. And finally, I showed you a small snapshot on practice-oriented models for seismic assessment of existing structures, where this essentially provide the basis for the new Chapter 9 in Eurocode 8 Part 3, which essentially relates to the second generation of Eurocodes, as well as current revisions on columns in particular in AAC 41 that essentially relate to the 2023 version. So with that, I think I'm right on time. I'd like to thank you very much for your kind attention. If something was not clear, I will be happy to answer to any question. Or if you feel that you'd like to know more, feel free to contact me. My email address, and I'll be happy to help you. So thank you so much. And I will, I guess, stop sharing my presentation, or you would like me to keep it?
I think we can keep it for now. Thank you so much, Professor Lignos. The presentation was very insightful, knowledgeable, and the database of your experimentation is very inspiring. We do get to learn a lot from it.
Thanks so much. Thanks.
Coming to the questions posted by our participants today, the first one is, how do we decide axial load ratio while conducting a cyclic test, and how it affects hysteretic curve or its behavior?
So the question relates to column testing or beam to column connection testing?
I think it will address to column, but it is not specifically mentioned it's for a joint or just column.
Yes. Okay. So maybe I can talk about both. So the axial load ratio. So for the experiments you saw, we selected the axial load ratio to range from something like 10% of the axial resistance of the column up to about we went up to about 75% of the axial resistance to of the column, which is quite excessive, of course, in this case. The way we decided on these axial load ratios is by conducting a survey in many designs that we reviewed on real buildings, but also on buildings that were designed either by people within my group as well as others. And essentially, this is how we selected those. Now, if the question relates to how you can conduct a test by selecting a rational axial load ratio, then I would advise that you have an archetype building or building in mind that maybe is reflecting the number of stories that we anticipate to have if it's a full-scale experiment. And then based on this number of stories, I would try to calculate what would be the load I would have to basically use it in the test. And if the question relates to connections, essentially it's the same thing, but now we don't test columns, we test the beam to column connection. And in this case, again, we would like to have a rational axial load ratio, but now at the beam to column connection. Now, I think there was a second part of the question, how the axial load, now I cannot hear you.
Yeah, second part is how the axial load ratio affects the hysteresis curve or its behavior.
Yes, yes. So if I go back to, maybe, I can, give me a second. If I go back to the, okay, if I go back to my presentation and maybe I show you one of the here the hysteretic curves. So what the axial load, so these tests, by the way, were conducted with an axial load ratio of about 30% of the axial strength of the column. So basically, if the axial load reduces, maybe I can sketch it here. What it will do, it will be easier for me to show it in the monotonic curve, but the axial load will I need a pen. So the axial load, what it will do, it will kind of rotate this curve inward. And essentially this difference here will be the axial load that you're putting times the amount of displacement that you have divided by the height of the column. So basically if the axial load becomes large, the hysteretic curve will move inward 0. If the axial load is less, essentially the hysteretic curve will move up. And if you have high axial load, that would limit your rotational capacity. It will make it obviously much smaller in this case. Okay. You have other question?
Yes, we have many.
Okay.
So next question is,
by the way, if you like, I can also share my slides. I'm happy to share a PDF copy of the slides, and if you think that you want to distribute them among the participants,
yes,
it would be no problem.
Yes, we will be we'll be putting up this today's presentation and your lecture on our YouTube channel.
Excellent.
Just for educational purpose. So yes, anyone who wants to see can see there. We will be emailing the link to all the participants and the members of our forum.
Okay, so other questions?
Yeah. So the next one, would your recommendations for web slenderness and axial D2C ratio hold true for short frames like 1 or 2 stories when the structural sizes are gravity dominated, as in a data center?
So, I mean, these recommendations you saw would be more so apply to the first story columns. So technically, we don't have any limit on the number of stories, but for a 2-story building or 3-story building, generally would be harder to go close to these limits. Usually, the axial load ratio, just to get an idea, of course, depends on the configuration, but the axial load ratio, I would say that it would be close maybe to 5 or 10%, so you would easily meet the limit. And then the web slenderness, of course, you may go near the compactness limit, but so there I would be a little careful. But if the design is not governed by something else, I think none of the two will actually control for a low-rise building.
Okay. Next question is, in the current Indian standard as well as the AISC seismic provisions and FEMA 350 do not permit the placement of shear studs within the expected plastic beam hinge region. What are your suggestions and recommendations related to whether to place or not to place these shear studs
Yes.
in the said plastic hinge regions?
Yes. So let me maybe go to this slide. So here, this image that I showed earlier, I think probably you still see it, right? We have done the same thing. We have not put shear studs within the dissipative zone, which is 1.5 times the depth of the beam. The reason why we try to avoid this is because if you weld a shear stud in this region, what could happen is that the weld itself could create a defect, and then this defect could potentially be problematic because this may induce fracture. So I think, this rule could, I think this rule could still remain like this. I think there is some additional work which was published recently by Professor Matt Etherton at Virginia Tech, where he did some tests and he was violating this by welding studs directly in this zone. And I think his observations confirm pretty much what I just showed you. So in short, I would not weld within that zone, but this is not so important when it comes to the leveraging the composite action, because I think what really matters is really what happens around the column and how the column face bears on the slab. So if you would like to leverage the composite action, you don't need the studs within the 1.5 depth, 1.5 times the depth, and you have to ensure that you don't prevent bearing of the column flange against the slab.
Okay. How can we assess the overall impact of residual stress due to welding on the behavior of a weld joint or a member joint?
So just to understand the question, so when we say residual stresses due to welding, we refer to built-up shapes, or we refer to welding in a welded beam-to-column connection?
I am not sure what
Oh,
the there is.
okay, so maybe I assume.
Maybe we can cover both.
Okay. So for the well, in both cases, in both cases, what happens is that there will be quality control, because you assume that you are respecting, for seismic applications, you are respecting some quality control criteria done by the fabricator. So based on the things that we've done and based on the assessment of residual stresses that we've looked for, let's say, good quality control criteria, the residual stresses should not be a concerning issue when it comes to welded joints. And the same thing goes for built-up shapes. Built-up shapes, though, are a little more complicated, because you have to pay attention into how the built-up shape is being created. And what I mean by this is that the residual stresses will look different if you are cutting the plate versus using the plate directly from manufacturing. But then again, I would not think that this will impact what the connection does. It would be more like a member issue and how the member behaves itself. Now I cannot hear you. I'm sorry.
I generally unmute myself so that you don't get it disturbed. What should be the limit on inelasticity in the panel zone?
Okay, so the current rules allow you to go up to 4 gamma y. Okay, And then if you talk to some of the offices, they will tell you that generally we prefer to keep it elastic because we're not certain, if you go to 4 gamma Y, what exactly it means. Now, based on the work that we've done, and also based on the review of the available tests on inelastic deformations in the panel zone, if you go up to about, I would say, 6 to 10 gamma Y, it should be okay. But you should also have in mind what is the corresponding drift level that we would like this to happen. So I would target something like 6 gamma Y, and I would target this at a drift level of about 3 to 4%, which is what we use typically as a drift level for a maximum considered earthquake, which is actually 1.5 times bigger than the design basis earthquake.
Okay, so the next question follows it. If we are allowing inelasticity in the panel zone, then what will be the possible ways to retrofit it post-earthquake? And also, how easy will it be to do it practically?
Yes. So I was expecting this question. This is a good question. So I think the way you should think about this is that if you allow inelasticity in the panel zone, if I play this video, let me just play this video again. I will explain this because it matters. Okay, so maybe let me clean here. I will give me 1 second, and I will answer the question in a minute. Okay, so if you, or maybe I can go direct. Okay, here we are. Okay, so let me try to see if I can erase it. Anyways, I cannot erase it, but I think this is how you can view this. Okay, so if you allow inelastic deformation in the panel zone, we have to think about repair. Okay, but this same repair, we also have to think in the case that the panel zone remains elastic and all the damage goes to the beam. Now, let's also consider the following. If we want to do repair, we are talking about an earthquake that will probably be the design level earthquake, not something that is extremely rare, because in this case, we will be looking at prevention of collapse, not so much repair. So if we talk about the design level earthquake, then we would be looking at the the drift in the order of 2 to 3%, as we see here. So if we review here the condition of the connection, as well as the panel, as well as pretty much the other side of the connection, that figure suggests that basically you don't need to do anything, okay? Whereas in the case where the panel zone is not elastic, in the case where the panel zone is elastic, you would experience much bigger damage near the beams. So in that case, you would probably have to do something for your beams. So I guess what I'm trying to say is that, when we are promoting inelastic deformation in the panel zone, shear yielding, basically you see here in this image that the only thing it does is that it kind of flux the paint. And the other thing that could be concerning is the fatigue life. But you saw that if I'm looking at the design level earthquake, the energy dissipation in the panel zone has been highlighted here. And at the end of my test, you see how far I can go. So that would suggest that I can actually dissipate the equivalent energy of at least 2 to 3 design level earthquakes without having to repair the panel zone.
Okay. Next is also in maximum panel zone area, there will be a transverse beam which will connect at the panel zone area. So considering the effect of transverse beam connecting the panel zone, is it possible to depend more on yielding in panel zone?
Yes, so that's a good question. So in fact, the transverse beam well, it depends on the configuration, but usually you will have a transverse beam. This is correct. The transverse beam, what will usually do is that it will increase a little bit the resistance of the joint. And you can, in fact, quantify this. This is something we are currently looking. But the good thing about the transverse beam is that the transverse beam works like a restrainer in the panel, because if you have a shear distortion in the panel zone and the panel zone deforms a lot more than you anticipate, then you may worry that, if the column you have is very slender, you may worry that you may get shear buckling in the panel. But the transverse beam, in fact, what it does, because it kind of separates the panel into two web panels, in this case, it works like a restrainer, and in fact, it will help the panel not to experience shear buckling. But on the strength side, I agree this is an issue, and we are currently looking into quantifying this. However, the equation I showed earlier, some of the tests that we had collected, in fact, had transverse beams in place, and we see that the equation basically works quite well, at least for these configurations that we have data. But we are currently doing some additional work on this.
Okay, moving on to the next question. To quantify the fracture potential of well-detailed discussed, why J integral EPFM is used and why not local approach methods like micromechanical based models is not used?
Okay, that's
and whether J integral is not valid under ultra low cycle fatigue.
Okay, that's a good. This is a good question. Give me a second to go into this. So here, here, I think you are referring to this. Let me see if I can delete those. Okay, so I think you are referring to this one. In terms of approaches, you could potentially use also a micromechanics based approach. I think by the time we started this, we did not have much information regarding these regions so that we can use a micromechanics based approach. But I think the way you should interpret the J integral and conventional fracture mechanics, because we have plasticity around this region, is that the fracture mechanics based approach, if you pick a micromechanics based approach, show that when you use the bevel will reduce the fracture potential. So if you want to use a different fracture metric, this is okay. But I think the way that we are using these results is not because we are trying to evaluate which fracture metric is the best, but we are trying to use a fracture metric that is rational, that shows that the fracture potential could be reduced if we do this fabrication trick. Okay. I think there is recent work, but also we are doing some recent work that in fact you could be using a micromechanics based model. The advantage would be, unlike the J integral, that you could evaluate the potential of say in this case this fabrication detail under cyclic loading conditions, whereas in our case here this was only done for monotonic loading, and then we did the experiment to kind of prove the concept and ensure that the beveled backing bar could work.
And now the last question of today's session. How has the variable axial load been applied in the column test? Is there a standard loading protocol that has been adopted, or does it depend on the specific analysis of the frame being considered?
Okay, this is another good question. So if I go back here, Yeah, so here for the constant axial load case, obviously, it's not an issue because we keep the axial load constant, assuming that we're testing the interior column. For the variable axial load case, what we did is that before doing the tests, we spent about 2 years and we analyzed about 90 or 88 frames, if I recall correctly, where we conducted extensive statistical studies to basically capture the axial load variation rationally. And what we did is we proposed the load protocol where, in addition to the lateral drift, we vary in a certain way the axial load ratio as well. So this would be in one of the publications that I'm listing down below, but feel free to contact me and I can point you also to the paper.
Thank you, Professor Lignos, for all your presentation and for this extended Q&A session. And if anyone has any other queries, we will not be taking them now, but you can send them to us at Structural Steel Education Forum, and we shall be sharing them with Professor Lignos.
Okay, well, thanks so much as well. And as I said, I can also send you my a PDF copy of my presentation. So in addition to the YouTube video, you could also feel free to share the slides, and I'll also be happy to discuss this further with any one of you, assuming we can also meet in person at some point.
Thank you, sir. Thank you so much.
Okay,
Yes,
thanks so much for the invitation again.
Thank you, Professor Lignos.